Progress is impossible without change, and those who cannot change their minds cannot change anything.
Hi, all. Dr. Clark here again, and today I'm going to continue talking about energy and matter. And this lecture is on both of those topics, okay? What does it mean when we say something has matter? What's the state that that material is in? What does it mean in the case of the field of environmental science when we say energy? Right? It means different things to different people, but I want you to think about what it means to a scientist and how we describe those different materials and what's kind of the definition of whether something has matter, whether something represents energy, because as we progress, we're going to start looking at ways that matter can be changed or ways at which energy can be utilized or developed. Right? So matter itself, we'll come back to this. Matter itself has a few states. Okay? It has a solid state, a liquid state, a gas state, and then often what we call the plasma state. Now, some of these states with different types of matter are not possible. Okay? Under conditions, normal conditions, it's not possible to have that state in a solid state, or it's not possible to have that state in a liquid state or a gas state or a plasma state. Okay, so we'll come back and look at that. That doesn't mean that all matter, you have to be able to have all these states at the same time or have that capability of creating all these states or developing all these states. Some are just not going to be possible. It doesn't mean that that material is not considered matter. Energy, on the other hand, a lot of people, when we talk about energy, they think about electricity. Electricity is not energy. Electricity is a type of energy. Okay? But when we talk about energy, I don't want you to just go to that place of, oh, he's talking about electricity. Okay? Energy comes in lots of different forms. Energy comes in what we call potential energy, which we'll come back to this, but potential energy is stored energy. Sometimes we're going to need to talk about that when we talk about renewable resources. When we talk about wind and solar electricity and water or hydroelectricity, we need to talk about how we're going to store that. Where's the potential energy? Because we're not running or collecting that energy all day, every hour of the day, you have to have a way to store it as potential energy. We'll talk about another form of energy, which we call kinetic energy, right? Or the energy in motion or of motion. Right? We'll come back to these. So energy itself is not electricity. Now, electricity is an example of energy, but there is a lot of other types of energy. For that matter, the food energy that goes into our bodies, or the solar energy that goes into a plant's tissues. Okay? Those are very different types of energy than electricity. We'll examine this. It'll make a lot more sense, and it'll give you a better idea of the connections between life and between technology. All right, so let's first dive into matter. We know that plant growth requires a combination of matter and energy. We know this because when we are talking about those previous experiments, John Baptist experiments, experiments done by early chemists, when we were talking about those experiments, one thing kind of connected them all. And they all mentioned that sunlight was allowing for the process to occur. Well, that sunlight, those photons, is a source of energy. Now, where does the material to build the tree come from? That comes from matter. Right? Different types of matter. In the case of some of the early chemists' research, it was coming from carbon dioxide. That carbon dioxide was being converted into starches or sugars or carbohydrates. Right? Now, the interesting thing about starches and sugars and carbohydrates from a perspective of you as a consumer, you might know that's energy for us. Okay? So that's the great thing about photosynthesis and the way that the energy flows is plants utilize photons from the sun to convert that carbon dioxide and water and some other things into sugars or carbohydrates, so then organisms that can't use photons from the sun can consume that material and still get the energy. We'll come back to this. Okay? That's part of the photosynthesis cellular respiration cycle. But back to matter. Matter is a physical substance that has mass and occupies space. So anything that has mass and occupies space is considered to be consist of matter. Now, at the current definition, photons are not included in this. Okay? Light wave patterns are not included in this because they don't have mass and they don't occupy. Well, I mean, in some cases it might occupy space. It just depends on the situation. Okay? Now, that being said, physicists have made solid light. Right, so they have made light in the form of one of the matter stages, okay, which would be to solidify it. Does that change the definition? Does that change whether or not light is matter? I don't know. It depends on who you talk to. Okay? But this is the great thing about science. Again, you have the capability to adjust your definition. Maybe we have to adjust the definition of what matter is. Or, in the future, maybe we should include things like light as having matter, even though it's not comprised of atoms. It's comprised of photons. Okay? We'll look at this. Okay? So mass is a measurement of the amount of matter an object has. Okay, so mass, or the weight an object has, okay, is how much matter that object has. So in this case, you can see here there's a beaker, so the glass, which is made up of molecules, okay, and then the water that's in the beaker. Okay, now, depending on where the water came from and what the source of the water was, it could be pure H2O or as close to pure H2O as possible. So that would be, the matter that occurs in that water. But if it came from, a faucet, or if it came from something like that, that water could have other things like salts in it. It could have other trace minerals in it. And it could have other additives like chlorine and things like that, which were added to it to make it, so microorganisms can't grow in it. Okay? So again, that still has a mass and it's still made of matter. Okay? It's just a combination of different matters, okay? Different products making that matter. Okay? The volume is a measurement of how much space an object takes up. Okay? Now this is interesting because at times we will take the volume of an organism to get at how much mass that organism has. Okay? Because there's a direct relationship between the mass of an object and the volume, or how much space it takes up. Okay? And I'll show you this in lab. Okay? It's a way that you can measure things that aren't, you're not able to put on a scale necessarily. Okay? So like aquatic organisms. So if you're to take a fish, you don't want to just throw a fish on the scale and see its mass that way. Well, maybe you do. Maybe you have a beaker that's got water that the fish can live in, and you can just put the fish in there and you can see how much mass it has. But another way to do that is have a known volume of water and drop a fish in it and see how much water is displaced by that fish. Both get at this relationship of matter. We'll come back to this and we'll look at it in future labs. Energy itself is the capacity to do work. So now again, energy can be in many different forms. Energy could be represented as a chemical that when you break it, energy is released, and that energy has the ability to do work. Energy can be represented as a photon or a light particle that can be captured, okay, and has the capacity to do work. Energy can be represented as, a large molecule that is stored and will eventually be broken down, but right now, maybe at this time, it's stored in the tissue of an organism as chemical energy or stored energy. And there's lots of ways at which energy can be represented. And I'm going to go through a few that are pertinent to environmental science. All right, so all matter in the universe is made up of atoms. This is where I came back and I said, look, we might have to change the definition of matter, maybe. Okay? We know that certain things might have states of matter, but does that mean they're actually matter? So if you can make solid light, and that's a state of matter, does that mean it has matter? Well, under the current definition of matter, no. Because light is not comprised of atoms. Atoms are the smallest units of life. Okay? And so an atom consists of three main characteristics. They have a nucleus, which consists of protons and neutrons. The proton determines the identity of that atom. So if let's say we have 6 protons, the identity of that atom is carbon. Now, the neutrons, the number of neutrons, identifies the mass of that atom. Okay? So the mass of that nucleus is based on how many protons you have and how many neutrons you have. It has nothing, right now it doesn't have anything to do with electrons because electrons don't have much of a mass. They do have a mass, but it's not very much, and right now it's not included in the mass of that element or the mass of that atom. This will play an important role because when we start talking about dating things, maybe we're going to start talking about radioisotope dating. Okay? An isotope is when this nucleus has a different number of protons to neutrons. So if we're talking about carbon itself and it has 6 protons and 6 neutrons, then it's known as carbon. Okay? And it's just represented as carbon, mass of 12. Okay. When we add neutrons to that, that's when we get molecules that most of you have probably heard before. Carbon-13, carbon-14. Okay? And we talk about using that to date things. Okay? We'll come back to this. I want to make your brains explode yet. Okay? But we'll come back to that in future lectures. But just realize that when we talk about matter, matter consists of these three things: protons, neutrons, that makes up the nucleus, and then electrons. Okay, so going back, just to kind of reiterate, protons have a positive charge, and they determine the atom's elemental identity. Okay? You change the number of protons, you change what element you're talking about. Okay? Electrons have a negative charge, and they orbit the nucleus. Okay? So they're attracted to the positive charge in the nucleus at times. Okay? There's an attraction there, especially if it's an isotope. The closer they are to the nucleus, the more attracted they are to the nucleus, to the charge of that nucleus. But they are rotating around this nucleus. They're moving in orbitals around this nucleus, okay? And they have a negative charge. That electron, or the behavior of those electrons, is what determines how that atom is going to react. So if you stick two atoms that have electrons, that are excited together, or if you split molecules and the electrons can easily be distributed to a different atom, then electrons can move. They can be moved from one atom to the next, from orbiting one nucleus to the next. They can also be shared differently. So let's say you're combining two things, and one thing has a high electronegativity, okay, which means it really, really wants to hold on to things. Then the electrons tend to stay in the region around that atom that has high electronegativity. The atom that doesn't have that high of electronegativity gets less time with the electron. Okay, less of the electron's orbital is around that other atom. We'll look at this when we start looking at molecules, how molecules are formed. We'll really dive into it when we start talking about polarity of atoms like water, or polarity of molecules like water. And neutrons, again, neutrons are neutral and also located in the nucleus. Neutrons determine, okay, kind of whether or not we're dealing with an isotope. And neutrons can change. How many neutrons you have in the nucleus can change, and when they do change, you're still dealing with the same atom. You're just changing the mass of that atom. Okay, so neutrons determine the mass of the atom. Okay, so hopefully that's not, that you're not too confused. Pretty simple process in the sense that all matter is made of atoms under our current definition. Atoms consist of three things: protons, electrons, and neutrons. Protons and neutrons make up the nucleus, and electrons make up the orbital, or make up the outside of the nucleus. Okay, so let's look at molecules. Molecules are a little bit different because molecules are when you're taking multiple atoms and you're combining them together. You can have simple molecules where it's just one atom and another atom combined together. And then you can have really, really complex molecules where you have tons and tons of atoms stringed together to make this really big molecule. We're going to look at both, and we're going to look at the complexity of some of these and why they're important to environmental science. So first, molecules are formed when two or more atoms are chemically bound together. Now, there are different ways to bond together. You can have polar covalent bonds, this is where we were talking before. They're sharing electrons. Here we have a hydrogen, and here we have a hydrogen. This little line indicates that there's a bond between them, that they're sharing a electron, single electron. Okay? Each one of these is sharing a single electron. But this is polar, which means one side has a positive charge or a more positive charge, and the other side has a negative charge or a more negative charge. If it has a negative charge, that would mean that that electron spends more time on this side than it does over here. Okay? And so that would mean that oxygen has a higher electronegativity than hydrogen does. Okay? Polar covalent bonds are very important, and in fact, they're important from the perspective of how life can occur on our planet. Really evolves around this molecule, the properties of water. Okay? And it's that polar covalent bond that gives water its unique properties. Non-polar covalent bonds, here you can see there's a line, 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 line. That means hydrogen is sharing electrons with carbon, but they're sharing them equally. Okay? So they spend time in orbit around each nucleus equally. Okay? So there's not a charge. It's a neutral molecule. Okay? And then here you can see also another example of non-polar covalent bonds, but now instead of a single electron being shared, you have two electrons being shared. You see the two lines? That's called a double bond. If there's three lines, it's called a triple bond. Okay? And you would have that number of electrons being shared between the two nucleus. Okay? Very basic. We're not diving deep into chemistry, but we got to know a little bit about chemistry so we can talk about how energy flows through a system, how energy can be considered bond energy. So what happens if you break this bond? Okay. Is energy released? How much energy do you have to break this bond? Okay. Same thing here. When you break this bond, is energy released? Okay. What else is released? What else can, an organism utilize to do work? Okay? Because remember, that's what we're talking about, is the energy portion is the ability to do work. These molecules often represent potential energy. Okay? In their form, they're potential energy. When you start messing with them and breaking their bonds, then they represent stored energy. And now you have that energy, and you can utilize that energy to do work. All right, so that kind of brings me to Joseph Presley. Okay, he was an English chemist, very prolific in publishing, published over 150 articles on different products in chemistry. Okay. And the first one that he discovered, the first kind of molecule that was discovered was by Joseph Presley, and it was discovered in a very simple experiment, okay, where he took a glass jar and he stuck a candle in it, a lit candle, and he put the glass jar over the top of the lit candle, and he watched what happened. And eventually the candle went out. Okay. Then he devised the experiment that was a little more complex, and he put a mouse in with it. Okay. So he repeated the experiment, and he put a mouse in with it, and concluded at the end of his experiment, after the mouse had died, okay, that the mouse was being injured by the air, or that the air had been injured. He then devised an experiment where he stuck a plant inside the glass case with a mouse. and found that the mouse would live much longer, significantly longer, if there was a plant present in the jar than if there was no plant present in the jar, or if there was a candle that went out and the mouse was in the jar. So he is getting at this connection between gases in the atmosphere and life on the planet. Presley had discovered the presence of oxygen molecules in the air. Okay. We now know that the composition of air is not just oxygen. Okay, and at the time, that's kind of what was thought, is oxygen was what was comprising that air during Presley's time. But now we know, because we have the capability of sampling air and looking at the composition of air, chemically looking at the composition of air. And we now know that 78% of the air is nitrogen. And we know that previous time on this planet, hundreds of millions of years ago, billions of years ago, nitrogen was far more abundant, okay, than it is today. Vice versa. We have 21% oxygen currently in the atmosphere. Okay? Give or take, depends on where you're at. Not give or take much, okay, but give or take a little. Depends on where you're at. But previously on the planet, okay, when we're talking maybe 2 billion years ago, maybe even 1 billion years ago, there is very little oxygen. In fact, the atmosphere was considered anoxic, no oxygen. Now, there might have been trace oxygen in the atmosphere, but it was so minute that organisms could not live on the planet. We have 0.03% carbon dioxide. Okay, so not very much carbon dioxide, although we know that when you increase carbon dioxide, you cause things to react to that, just like if we decreased how much oxygen or decreased how much nitrogen or increased how much nitrogen is in the atmosphere. Anytime you tweak these numbers, situations can occur. Okay. We have about 0.02% water in the atmosphere. Okay. Again, it depends on where the measurement is being taken. Okay. If you're taking it over the ocean where water is being evaporated up, you might have a little bit higher numbers than if you're taking it, over the Sierra Desert or Sonoran Desert or Chihuahuan Desert. You might have less water in the atmosphere, or in the air. Okay, but in general, these numbers are fairly stable. Okay, and then there is a small handful of other gases. Okay, but these are the four main players: nitrogen at 78%, oxygen at 21%, water at 0.02%, and carbon dioxide at 0.03%. So, to an environmental scientist or to a biologist, what is energy at the molecular level? There are kind of three ways to look at energy in this course, okay? And it evolves around these ideas. Okay? Photons is an energetic source. Now remember, right now, photons are not matter. So photons are not part of matter, okay? But photons are an important energy source. Okay? So light is what we're talking about when we're talking about photons. Electrons. Okay? Electrons are associated or are a component of matter, okay? Because they're associated with an atom. Okay? So electrons, that negatively charged electron that orbits the nucleus of an atom. So sometimes in here we're going to be talking about photons as energy. Sometimes we're going to be talking about electrons as energy. And then sometimes we're going to be talking about macromolecules like adenosine triphosphate, or what's normally called ATP. And ATP is the molecule that we use to drive work in our bodies. It's the molecule that plants use to drive work in their bodies. It's the molecule that bacteria use to drive work in its body or its cell. So ATP is really the result of the two up here, photons and electrons. The energy from photons and electrons are utilized to form this molecule, adenosine triphosphate. Okay? And yes, at first when you're looking at this molecule, like, oh man, that is so complex. This is ridiculous. What have I got myself into? Okay? But adenosine triphosphate is a simple molecule when we start talking about the grand schemes of macromolecules. When we start talking about how things are put together, adenosine triphosphate is actually relatively simple. Okay? So don't get scared when you're looking at these molecules. We'll talk about, what does this mean? What are these carbon rings, and what are these bonds? What do these numbers mean? Okay, what's the P's? Okay, but some of these you already know, like that double bond. There's a phosphorus double bonded to oxygen. Okay, now the key component to adenosine triphosphate, we'll come back to it, but one of the key components that makes it such a unique energy molecule is these phosphates. They all have negative charges, but they're all bound together. So you're binding three negatives together. This does not want to stay together. This does not want to be held together. It wants to come apart. It wants to break and release energy. And that's what makes it very unique to our system. It's like stacking three negatively charged magnets and pushing those negative charges together. And you know that they're forcing it back, but you're holding it there just to release it and have them slam apart. Okay? Adenosine triphosphate, a great molecule. We're going to talk about how things get converted into adenosine triphosphate, how glucose or carbohydrates get converted, how proteins get converted, how nucleic acids get converted, how fats get converted. Because when we consume food, it's not made of a bunch of ATP molecules. It's made of much larger molecules, complex carbohydrates, starches, and glucose, and fructose, and sucrose, proteins, lots of different types of proteins, lots of different types of fats, unsaturated, saturated fats. And when you consume it, your body is going to then convert it into smaller molecules, breaking bonds, cleaving off things, rebonding things, until in the end, you get this, ATP. All right, next we're going to talk about energy.